Okay, last page of the practice test. We'll start with number 16 here. So Connor dives off a bridge in the river. Explain why he spins faster if he pulls his knees to his chest. And we kind of talked about that one before. When you tuck in, you decrease your rotational inertia. So you decrease your rotational inertia because that typically goes something like your mass times the radius squared. Radius really counts. If you pull your arms in and stuff, your kind of effective radius, your size is smaller. It decreases by squared. Your angular momentum stays the same. So angular momentum, because you're in the air, right? Nothing can stop your angular momentum, no friction or anything. Angular momentum stays the same. So that's L is equal to I omega. If L stays the same and if I gets smaller, then omega has to get bigger. So you speed up, you go faster, right? Omega is your angular rotation rate, how many degrees per second you spin, or rotations per minute, right? It's an angular velocity, how fast you spin. Anyway, so if I gets bigger, I get smaller, rotational inertia gets smaller, omega has to get bigger since your angular momentum stays the same. Since you're in the air, you can't lose your angular momentum to the earth or anything. Okay, that's 16, hope that makes sense. Number 17, you're going around a turn. Okay, so let's look at that. So let's say that here's a car, we're looking from an airplane. Here's the car from the top, right? And you're going around, you want to go around a turn. Okay, cars want to go straight. So there has to be a force, right? There has to be a centripetal force making you go around that turn. If it's icy or something, you can turn the wheel and it doesn't matter, right? You're going to keep going straight. There has to be a frictional force. There has to be a force on, then what does it act on? The tires, right? It acts on the tires because that's where you're touching the road. But we know that forces acting in the tires are like lever arms about the center of mass. So now if I draw, like imagine the car is right here now. So if I draw a picture of the car from the side, so here's our car. Okay, and imagine this, here's the wheel. The wheel is just going around a turn. So let's say it's going this way, right? So we're going around a turn here. There is a force keeping it going around the turn, and that force is acting on the tires, like we said. So it's pushing inwards on the tires. It's forcing the car, like here, it's forcing the car to go around the turn, forcing the car to go around the turn. Let me think. Really, it's coming in from, we're looking at the right side of the car, so the force is coming in this way. So the way you draw that, if you draw a circle with a dot in the middle, that's like an arrow, it's coming out of the board. That's a force coming out at you. The way to draw a force going in is you draw like the tail feathers, you draw an X. That represents a force going in, because I can't really draw an arrow here, right? It's coming out at us. So right here on the tires, there's a force coming out at us, making the car go around the corner, forcing it inwards. Well, the car wants to rotate about the center of mass. Okay, so if you push a force here, then we can imagine before, like we draw a bar like this, the force is coming out at us. So what's that's going to do? It's going to turn the car, it's going to want to turn the car this way. Okay, try to imagine that, the force coming out this way. So there's the bar, so we're turning the bar like this. And the same thing in the front tire. We're turning the bar like this, which means the car is going to want to flip over to the outside. The car is going to want to flip over to the outside. So let's imagine this picture here again. Here I can draw the arrows, right? So there's these forces, these two arrows are acting on the tires of the car. It wants to rotate about center mass, which is above, right? Somewhere above the road in the car right here. And so let's draw center mass here. There's an arm goes to that thing, and so you're pushing this way, and it's going to want to rotate the car over that way. So your car flips to the outside. It's a hard picture to draw. It's probably trying to think of a better way to do that, but But same idea as kind of as when you slow down and speed up, that then it's a forwards backwards. If you're going around a turn, the force is this way, and it makes the car want to flip to the outside. The higher the center of mass, the longer the lever arm, the more it's going to want to tip over. So you don't want to have a high center mass or the cars tip over easy. That's why racing cars are really low to the ground and everything, so they can take corners super fast and not tip over. So that, yeah. Okay, that's the next one here. So high center mass means longer lever arm, and so then it tips over easier. So was that one. Off-road cars is, you try to, well, they have high center masses because they want to have big wheels to get off the road, but then they tip over easier. So it's a compromise you make. Okay, number 19. Oh, this one. So you pull a spool of rope towards you horizontally, go towards you. Watch the video on this. Remember, it's really tricky. So let's see. So here's our spool. Okay, and then there's a core here, so here's where it's along the ground. And let's say it's coming out here, here's your string, so you pull the string here. Which way is it going to turn? Now it's touching the ground here. There's got to be friction. Okay, there's no friction, and this isn't the case, but there's friction against the ground here. So it's pivoting about this point. We're pulling here. There's a lever arm, like this. So it's rotating about this point. So if you pull like that on a lever arm, it's going to rotate now. So which way is this spool going to go? Let's see, we're going like this. So there's going to be a clockwise torque, so it's going to roll towards you. Okay, if you pull the top of the spool. So let's see if we draw the same picture, and now we pull the bottom of the spool. So now let's say the rope comes off the bottom, it's around this way, so we pull this way here. It's still rotating about that lever arm, and if we pull it, it still goes, right? It's the same difference. It's a smaller lever arm, right? It's a smaller lever arm here, so maybe the torque won't be as big, but it's still a torque that wants to turn it this way, so it's still going to go towards you. So it doesn't matter which way, if it's coming out the top or the bottom, as long as there's friction out. There's no friction here. If it's really slippery, then it doesn't happen. We're saying there's a point here where it's rotating about, the frictional point here, and it goes towards you. And you should try that out. But again, there's got to be friction. If it slides along a slippery table, it doesn't always work. All right, so you walk across a slack line or a log across a stream. Instinctively, you put your arms out. So you might think that's a bad idea to do, because if you put your arms out, right, so here's Serena here, you put your arms out to the side. We'll give her some long arms. Okay, I shouldn't have drawn the short little arms there. Then you're raising your center of gravity, your center of mass, which is bad, because when you raise your center of mass, you're more likely to topple over, right? You're not as stable. So you'd think maybe that's a bad idea. However, remember, rotational inertia is proportional to the mass times the radius squared. Your mass is staying the same, of course, but your effective radius of your body is increased, and so therefore you're less likely, you increase your rotational inertia, which makes it harder to rotate. Okay, so if her arms are spread out like that, it's going to be harder for her to rotate back and forth this way, because her rotational inertia, her resistance to rotating, is greater, because you increase your rotational inertia. So if you throw your arms out while walking across a log, you rotate slower from side to side, which means you can, if you start tilting one way, since you rotate slowly, you can catch yourself and push off on the log and put your weight back to the middle. Okay, so the idea is here, you increase your rotational inertia, which we know is letter I. So therefore you decrease, or you make it harder to rotate, so you make rotation rate kind of smaller if you happen to lose your balance and turn, so therefore you can recover easily. You don't quickly fall over. it takes a long time to fall over. That's why tightrope walkers will carry a long pole. The ideal pole would be something that's low, so you carry a pole like this, where it's got weight at the end, as far out as possible, as long a pole as possible, and you hold it in the middle. The weights are low, so that your center of gravity is low, which means that your lever arm is shorter, because right, you're rotating about the place where your feet are touching the log or the rope, whatever. So you have a short lever arm, because your center mass is low, and it's hard to turn because you have these heavy weights. This is really difficult to turn back and forth, so you don't tip over very quickly. Which is like number 21, and I think most of you guys have seen that eagle I have in class, and you can put the beak on your finger, and it can swing back and forth and everything, and it doesn't tip over. So first off, it's got weights in the wings. It's got these lead weights in the wings, and the wings are sloped downwards, and then in the tips of the wings, I should say, in the tips of the wings. So in the tips of the wings, what those do is they're low, so they make it a low center of mass or center of gravity. Again, pretty much the same thing. The only time they're not the same thing is if gravity is changing rapidly. Then it might change, but on Earth, gravity doesn't change rapidly. It's pretty much 9.8 everywhere, so it's the same thing. So they have a low center of gravity, which means that if it starts tilting, if the wings start tilting, you actually raise the center of gravity, and the center of gravity wants to go low, so it immediately goes back down. So the center of gravity is actually below the beak. That's a critical point. The center of gravity is below the beak. If the wings tilt to one side, it raises the center of gravity. They just want to go back down to where it was. Or if it goes side to side too. So the beak is up high, the center of gravity is low. That makes it very, very stable. Just like a tightrope walker where he can have the center of gravity below the rope. Normally you can't do that on the ground, right? I can't have my center of gravity below my feet. You got to be above the ground. But if you're on a tightrope or the beak or something, you can have the center of gravity below the balance point. That makes it really stable, because if it goes back and forth, you're raising the center of gravity and wants to go back down. The other reason is, again, it's got a high rotational inertia because the weights are on the tips, right? That's why I said this here. The weights on the tips, so it spins slowly. So it starts slowly, goes over one way, and then comes back the other way. So because the weights are at the end of the wings, and they're at the end of the wings for two reasons: to have a high rotational inertia, but also then to get the weights as low as possible at the very ends of the wings. Okay, so spin slowly and has low center of gravity. And almost done here, number 22. So torque, the lever arm is 0.3 meters long, 40 Newton force at a 45-degree angle to the lever arm. Okay, so here's our arm, this is 0.3 meters. And we exert a force on it, but it's at 45 degrees. So here's our 40 Newton force, but it's at 45 degrees. So it's only okay, it's exerted right here at 3 newtons, right? So here's our pivot point. Here's our arrow. But it's only the perpendicular force that matters. Part of that force is being wasted stretching out our lever arm, which isn't really what we want to do. So we got to figure out what this side is. This is the force. My picture is kind of small there. That force there, the perpendicular force of the lever arm, that's the one that makes it want to turn. Okay, so let's see. We know the hypotenuse is 40. This is opposite. The opposite is F. So sine of 45 degrees is opposite. Opposite the 45-degree angle is what we want. This force here, the perpendicular force, is F over 40 newtons. Hypotenuse, right? Opposite over hypotenuse. Or the force is 40 newtons times the sine of 45 degrees. That's the force that's actually doing the turning. So you plug that into your calculator. 45 sine times 40, and I get 28.28, so 28.28 newtons. So the torque then, it's just R times F, and again, as long as these R's and F's are at right angles, you can use this, and we already did because we figured out that this force is at right angles. So it is 0.3 meters times 28.28 newtons. I get 8.49, let's say 8.5. So about 8.5, and the units of torque are Newton meters. In the English units, they're foot-pounds, distance times a force. So foot-pounds, here we're multiplying newtons by meters, so Newton meters. So that's the strength of the torque. Okay, now find the energy required to turn the above bolt 60 degrees. Okay, so energy, we know from before, is like work. So energy is like work, which is the force times the distance, which here, the force is a turning force, torque, times the distance. You turn something a distance of an angle, so times the angle you turn it, times theta. The units are the same, right? Torque is Newton meters, and force, work, is Newton, F times meter, distance meter. So torque is Newton meters, and theta has to be in radians for this to work. And then the units are Newton meters, because radians, if it's a natural unit, doesn't really count. So we just put 60 degrees in radians and use our torque from up here, 8.5 Newton meters. So that's 8.5 Newton meters times 60 degrees. We have to have in radians. So the way, remember, you convert radians is you take your degrees and you multiply by pi. Radians is the same as 180 degrees. You always put what you want at the top. We want the radians at the top, put the pi on the top. Degrees cancel. So that's 60 divided by 180 is 3, so that's pi over 3. So times pi over 3. And so we just go 8.5 times pi over 3. So times pi divided by 3. And I get about 8.9. So about 8.9, which makes sense, right? Pi is about a little over 3. So it's just going to be a little over 1, it makes it a little bigger. And it is, the unit is joules, because a Newton meter is a joule, force times distance. So torque has the same units as joules, which is kind of interesting, even though it's kind of a completely different thing. So 8.9 joules is the answer. That's how much energy it takes. Force times distance, or torque times the angular distance times the angle, has to be in radians. Okay. Okay. My voice keeps going away, but came back, fortunately. Hope that makes sense. Now we're done to the practice test. And the real test is coming.